Okay, so the question says, now all of a sudden, hold on. Okay, so it's a little more complicated even than I remember it being. So the question says, let V equal the set x1, x2, x3. Oh, I wanted to write with a smaller pen and see if that made my handwriting better. So I'll try x4, x5. Okay. It's crooked. Why am I writing crooked? Oh, because the pad is crooked. Okay. And then is an element of R5 such that x1 minus, x3 plus 2x5 equals 0. So that's our set. And we got a set B1. Okay, B1 is 1, 1, minus 1, 1, minus 1. And there's two vectors in it, so that one's the first one. And then 1, 0, 2, 2, 1 is our second vector. And the question's saying extend B1, so extend B1 to a basis for B. It's for V. To a basis for V. And it says, note, this is only possible since B1 is already linearly independent. Okay, so it's linearly independent already, so we know that. Now, how exactly did he do this? Let me see. Oh, hold on. No, this is not the question I was thinking of. This is the question I was thinking of. Sorry. But maybe I'll do this question after, because this also seems like, but we should start with this other one here, too. Okay. So, sorry. The question I was thinking of, less writing on it, too, so it's okay. Let V equal the span of 2, 1, 1, 0. Yeah, I remember it being a R4 one. And then 1, 1, 1, minus 1. So V is that span. Okay, assuming these are linearly independent. Okay, so this forms a basis for V. Extend this to a basis for R4. So the question is, extend this span to a basis for R4. Expand this basis to a basis for R4. Extend this. Okay, basis for R4. Okay, so to do that, you're going to take the first two vectors, so 2, 1, 1, 0, and 1, 1, 1, minus 1, right? So that's these two vectors. And attach onto the side the standard basis. This one. Standard basis for R4. Right? And then from here, well, so the reason you do that is because you want to see what you want to see what's the basis for, I guess, for the column space of it, right? So you want to see the any linear dependencies in the column space. So I don't have all the steps written because whenever Horowitz does RREF, I just write the final RREF. So if you do it, you're going to end up with this: 1, 0, 0, 0, 1, 1, 0, 0, 1. I mean 0, 0, 1, 0, 1, 0, minus 2, 1. Is that a minus 2? Who knows? That doesn't really matter, actually. 0, 0, 0, minus 1, 0, minus 1, minus 1, 0. Okay, so after RREF, it's here. Or not even RREF, just REF. And so now you can see which ones have the leading entries, right? So that means we choose, right? We choose these four. 1, 2, 3, 4, right? And so, so you're given three vectors. Would you put all three in? Yeah, you'd put all three in the matrix, right? You'd put all three. And then put on the standard basis that you're trying to extend to, right? and then do this because this points out all the linear dependencies, right? These two are linearly dependent to the rest, or I don't know if I'm using the right words there, but so these two don't count. They don't add anything to the span, right? So you don't count them, and you can tell because after you do REF, they don't have a leading entry in their column. So the answer is this, right? Is this, and so notice our answer. The question is a subset of our answer, right? These two vectors are a subset of our answer, and that's kind of the point, right? You extended the starting question to be a subset, as a subset of your answer. So maybe let's do the other one here. Let's do the other one here because it's string. The yellow ones I highlighted here. These vectors that I highlighted here. Those. Yeah, and that spans R4. The span of these 4 vectors is R4. So what we did is we pretty much, so the span, right? The span is every combination of the vectors, right? Everywhere they can possibly reach, right? Addition and multiplication, right? So right now, this span is R2, right? So it's some slice of R2, right? Because we know they're independent, right? So we want to pretty much take that slice of R2, add on 2 more vectors that are independent from the rest, right? Independent from the rest, so that it spans R4 now. Because any basis for R4 is going to have 4 vectors in it. Does that make sense? So what I did is I took one basis I already know. I know this is a basis. This is a basis right here, right? And I stuck on the 2 vectors that I want to be in the basis. And so I know that 2 of these, some 2 in there, are not going to be, are going to have to be canceled out, are going to be dependent, because R4, any basis for R4 has only 4 vectors in it, right? So there's no way that this is a basis for R4 because it has 6 vectors in it, right? So what that means is that 2 vectors are not adding anything to the span here. 2 vectors are not, and it's specifically these 2 are not adding anything to the span. Not adding. Right? And so they're dependent. They're linearly dependent. So we don't count those, and we only count the ones that have the leading ones in the REF or REF. Okay. So that's how we do that. It has to do with column space. I don't quite understand it that much, so maybe tomorrow once I do some 4.11 practice. Oh no, but column space isn't even 4.11, so I did 4.10 practice already. I don't know. That's it. Yeah, sure, I can do that. The shortest distance between non-parallel lines, they were difficult, and I did them. They were difficult questions, though. Definitely had to look it up, like look up how to do it. Okay, but let me do this one here. This one, that other one from Horowitz. So it's this up here. Maybe I'll rewrite it. I'll rewrite it down here. So the question says V. It's giving us V is. I'll just write like this because I'm lazy. So, well, no, actually, I shouldn't write like that. Never mind. I'll write x1, x2, x3, x4, x5. Okay. So we are in R5, okay, under the condition that x, the glare for some reason, x1 minus x3 plus 2x5 equals 0. And the question, so that's just a subspace, right? The question is saying let B1, well, that's not a question yet, but so it gives us let B1 equal 1, 1, minus 1, 1, minus 1, and 0, 1, 2, 2, 1. Okay, and extend B1 to be a basis for V. Okay. So another way to write v is if we take this condition here. If we take this condition right here, and I rearrange it for one of the variables, so I can say maybe x3 equals x1 plus 2x5. So I can rewrite this down here as v equals, so it'll be x1, x2. Now we notice x3 is equal to x1 plus 2x5, so I'll write that x1 plus 2x5, x4, x5. Okay, so we now have included the condition in there, right? So we're in R5, and there's no more conditions, right? There's no more. We've included the condition, right? So we don't actually have to write this anymore. So it's a little simpler now because we can just extend B1 to be a basis for this, and it's a little easier. So what we need to do, like before, how we said, well, we took these two vectors, put on a basis that we know, right? A basis that we know, put that in a matrix, and then row reduced, right? That's how we did it. Or it doesn't have to be RREF, just REF. We row reduced. Well, we're going to do that here too. We're going to put these two vectors, put it onto a basis of this, right? Basis of this. So this isn't just R5. The last one was just R4, so we could just put the standard basis. But this is a specific subspace. So I need to find the basis for this. So one way to find the basis for this is, well, the only way I know is, right, so a basis it means that we can write any of these vectors as a linear combination of those basis vectors. So let's write that as a linear combination. x1, 1, 0, 1, 0, 0. Right, so I didn't use the right words to go from here to here, but hopefully you can see what I'm doing, right? So all the rows with a 1 in it, with an x1 in it, get a 1, 0. This has an x1 in it, so it's a 1, 0, 0, plus x2, so 0, 1, 0, 0, 0, plus x3, 0, 0, all zeros. Right, all zeros here. None of these terms have an x3 in it. x4, 0, 0, 0, 1, 0. Right, and then x5 is 0, 0, 1, 0, 0, 2, 0, 1. 0, 1. So notice we can write any vector in V as a linear combination of these vectors, which means that these vectors form a basis for V. Okay, so basis for V is, one of them is 1, 0, 1, 0, 0. Oh, sorry, I said that like that was the last one. And the rest of the vectors too. Right? So first vector, this vector doesn't help, right? So it would be dependent with that. Right? So then 0, 0, 0, 1, 0. And I'm thinking now, can I assume that these are linearly independent? Let me look at the work. I think I can. Yes, I can assume that they're linearly independent. Can I explain that? I don't know, but I just have a feeling that it's, yeah, I just have a feeling. Notice that the dimensions of V is 4, right? Dimensions, doesn't matter, but just dimensions of V. I think my handwriting is a little better with the smaller thing, so. I don't know if anybody recognizes that my handwriting is better. Let me know. I think it's a little better. So they are independent because each row has 1 and everything else is 0. Oh yeah, each row has 1 and everything else is 0. Not the third row, but yeah. Yeah. I see what you're saying. Yeah. Okay, so then now I know a basis for V. And I know what I want to extend into a basis for V. So I'm going to do this. I'm going to take these two vectors, 1, 1, I have it on my page here. So 1, 1, negative 1, 1, negative 1. Yeah. I'm going to put the other vector there too. 0, 1, 2, 2, 1. Let me just make sure I wrote that right. Yeah. And I'm going to put on this basis for V. So it's going to be 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. 0, 0, 0, 1, 0, 00201. Okay, we got a big matrix here. I'm going to put that. Oh, hold on. This is not what he did. Let me see what he did. He wrote -1. Okay, this is not what he did now. He did like something different, but I think this might still work. Theorem of VR subspaces. Let's just try it and see if it works. This isn't how he did it, so if it doesn't work, then I'll do it a different way. I know it's confusing. Anyways, so he didn't do the REF for this one, so let's see. I'm doing. This is the question number 2, right? So the first question we finished. This one was pretty short actually. Well, because I didn't have to do it. So this question is finished. Then I started another one with this subspace. Right. So I'm going to REF this. So it's going to be. Well, I found the basis for V, but what I want is a basis for V that includes B1, the set B1 here. Right? So that's what it means, extending B1 to be a basis for V. Right? So it's some basis for V. Right? There's infinitely many bases for V. And I want specifically one that includes these two starting vectors. Yeah. So hopefully this works. If not, then I'm confused. So R2 minus R1, R3 plus R1, R3 plus R1, R4 minus R1, R5 plus R1. So 1, 0, 1, 0, 0, 0. So 0, 1 minus 0 is 1, 0 minus 1 is -1, 1 minus 0 is 1, 0, 0. Add the two, so 0, 2, 2, 0, 0, 2. 0, 2, minus 1, 0, 1, 0. And then add it. So 0, 1, 1, 0, 0, oops, 1. Almost wrote a 0 there. Okay, now I will do row 3 minus 2, row 2, and row 4 minus 2, row 2, and row 5 minus row 2. Right, so 1, 0, 1, 0, 0, 0, 0, 1, minus 1, 1, 0, 0, 0. So 2 minus 2 is 0. 2 plus 2 is 4. 0 minus 2 is -2. 0 minus 0 is 0. 2 minus 0 is 2. 0. So 2 minus 2 is 0. -1 plus 2 is 1. 0 minus 2 is -2. 1 minus 0 is 1. 0 minus 0 is 0. Then 0. 1 minus 1 is 0. 1 plus 1 is 2. 0 minus 1 is -1. 0, 0, and 1. Okay. So I can already tell these two rows are the same, right? Those two rows there are the same. So I will do well, I guess I'll just do this. I'll do 1 half row 3 minus nope, that's not what I meant to do. Row 5 minus a half row 3. Or yeah, minus a half row 3. Yeah. And then I'll do row 4 row 4 minus let's just deal with that first. Too much stuff happening in one step. I mean, not even that much, but I'm going to get confused. So let me just do this. 0, 1, -1, 1, 0, 0, 0, 0. And I'm not really supposed to, but in the same step, I'm going to turn this into 2 minus 1, 0, 2, minus positive 1, 0, 0, 1, minus 2, 1, 0, and this is just going to be a row of zeros on the bottom now. Okay. And now I will just do, I guess I'll do row 3 minus 2 row 4. Row 3 minus 2 row 4. Let's see where that takes us. So 1, 0, 1, 0, 0, 0. 1, 0, 1, minus 1, 1, 0, 0. Okay, so 0, 0, 2 minus 2 is 0. Negative 1 plus 4. Negative 1 plus 4 is 3. 0 minus 2 is minus 2. 1 minus 0 is 1. 0, 0, 1, minus 2, 1, 0. 0, 0, 0, 0, 0, 0. Okay. So, well, yeah, I'm like one step away. Let me just check the answer quickly, see if I did everything right. Yeah, it worked. Okay, good. We're good. It did work. So I'll just, these will have leading entries, right? I really should reorder this, but those are the ones with leading entries. There won't be any more leading entries. So what that means is that we need to choose 1 to 4 from our starting set, from this starting position. So that means the basis, so let me just say, this is our answer. These 4 vectors, those starting 4 vectors. And those starting 4 vectors are a basis for V that includes B1. So B1 is 1, 1, 1, minus 1. That's these. This is B1. B1. That's a basis for perfect spot. Basis for V, right? That whole thing is a basis for V, right? That includes B1 as a subset. So B1 is a subset of the basis for V. It already is, but sorry, it already is a subset for the basis for V, but we specifically showed one. That is a subset. Okay. So yeah, that's that. Apparently other teachers didn't do it, but we definitely did it. Although this was actually taught before column space and row space, so maybe not. Well, who knows? Just see what other stuff there is here. I don't know what sometimes when Horowitz does, I just realize when Horowitz does question, or maybe I'm just not writing it. No, I'm probably writing it. Yeah, that makes sense. How did I can do some questions that are like finding. I kind of want to practice it too, like finding the basis, for like when you start with this, like find the basis for this set, or this subspace. Does anybody want me to do a question like that? I have an example here. Could do it. If not, I'll do this question here. Nicholson problem: shortest distance between non-parallel lines. Or if anyone's got any other questions. Okay, I might do one of these after. So, okay. So I will do the shortest distance between two parallel lines now, or non-parallel lines. So the question says, well, it says what I just said. Find the distance, the shortest distance between two non-parallel lines and find the point that's closest. Find the point on each. Yeah, find the point on each line that is the closest. Okay, So we're given two lines. So our first line is this in R3, 3, 1, minus 1, plus S. I don't like S, so I'm going to say R, because my 5s look like S's, so I'll just do this. So 1, 1, minus 1. So R times that. And the other line is X, 1, 2, 0, plus T times 102. So I might have to stop for a second and either look at my solution for this or look up one part of how to do it. But I do remember the beginning at least. So the thing that didn't quite make that much sense to me when I first started approach this problem is that, well, okay, we're looking for, we have two non-parallel lines, okay? So we don't know. These might intersect somewhere. Well, first of all, they might intersect somewhere. So that's okay. Let's check if they intersect. Check if they intersect. Because if they intersect, then of course that's the closest point between them because they intersect there. Can't be closer than that, right? So that's what I would do first. But assuming they don't intersect, that means that there's some distance that we're looking for, right, between these two lines. That's the shortest distance, right? That's the shortest distance. And then of course find the points, right? So what wasn't obvious to me at first is that this is the cross product of the two direction vectors. The direction of that is the cross product. So direction of yellow equals D1 cross D2. Maybe that's obvious to someone else. That wasn't obvious to me. So my kind of explanation for it is if you were to squish them together, they would form a plane, right? And so that kind of like that rail that you're squishing them together on, right? But you can't like move them side to side, but just pushing them together so that they touch. That's normal to that plane that they make when you put them together, right? So so then if that's normal, if that rail is normal, then that distance is the cross product of the two direction vectors. That might make sense. So let's do the cross product of the direction vectors. 1, 1, minus 1, 1, 1, minus 1, 1, 1, minus 1, 102. Okay, so let's cross these. So 2, so 2. Negative 1, minus 2, 0, minus 1. Okay, so that's the direction that the shortest distance will be going in. That's something. So, and I'm going a little bit off of memory here completely. I mean, of course I'm going off memory, but vaguely remembering how I did this. So if I screw up and have to go back, then we might do that. But what I remember doing is, let's just choose an arbitrary point on this, call it A. Let's choose an arbitrary point on this, call it B. Okay? Any point on this line, so I'll say L1 is that, and L2. So this is L1, and this is L2. Any point on L1 can be represented as this. X is equal to 3 plus R. Y is equal to 1 plus R. Z is equal to negative 1 minus R, right? Just from the vector formula. And this is the parametric form, right? This is the parametric form. Same thing for this one. I can do that same thing over here. So I'll write it up here. So X equals 1 plus T. Y equals 2, and Z equals 2t. In other words, any point, this point A, right, can be written as 3 plus R, 1 plus R, minus 1 minus R. That's A. I just call it, name it on the wrong side, but that's A. Similarly, B is just 1 plus T, 1 plus T, 2t. So we have two arbitrary non-specific points one on each line, A and B. So let's find AB. Let's find AB. Right? So AB is B minus A. Right? So that's going to be equal to 1 plus T minus 3 minus R. Right? So that's negative 2 plus T minus R. So 1 minus 3 plus T minus R. Okay. 2 minus that So 2 minus that is going to be 1 minus r. And 2t minus that is just going to be 2t minus 1, plus 1 plus r. So now we have AB. And one thing we know is that AB is going to be orthogonal to both direction vectors. AB is going to be orthogonal to both direction vectors. Right, so that's AB. Of course, if I just called this, sorry, I just should have called that A and that B, right? But again, that's arbitrary, so it doesn't matter at all. Right? That's A, that's B. So then these line extensions don't mean anything. So now we have AB, right? It's this point right here. Well, the thing we know about this point is that AB is going to be orthogonal to both those things. Right? So I take AB, so I'm going to write it down here. Minus 2 plus t minus r, 1 minus r, 2t plus 1 plus r. And I know that when I dot this with the first direction vector, which was 1, 1, minus 1, I'm going to get 0. In other words, minus 2 plus t minus r plus 1 minus r plus 2t plus 1 plus r equals 0. Okay, one equation. Let's do the other one. Minus 2 plus t minus r, 1 minus r, 2t plus 1 plus r. I guess my r's kind of look like v's, so maybe I should choose a different letter too. And I'm going to dot that with the second direction vector, so 1, 0, 2. I'm just going to make sure that was right. 1, 0, 2. So I'm dotting that with the second direction vector. Well, so I know. Oops, this is supposed to be negative. I made a mistake here. This is supposed to be, just realized, this is supposed to be minus 2t minus 1 minus r equals 0. Yeah. I just before you said that, notice it. Then this one is going to be minus 2 plus t minus r plus 4t plus 2 plus 2r. And that's going to be equal to 0 as well. Okay, let's collect some like terms. Maybe I'll collect like terms up here. So let's do the t's first. That's a t there. So we have a t and a negative 2t, so that's negative t. Okay, then so the t's are done. R's, negative 3r. Okay, these cancel. And just minus 2 equals 0. Okay. Then here, let's look at the t's. So I have t, 5t, so just 5t. Negative r and 2r, so that's just plus r. Okay, and then the 2's cancel. That equals 0. Well, two equations, two unknowns, we can solve for this, right? So r equals negative 5t. Put that into here. Negative t minus 3 negative 5t minus 2 equals 0, right? Because it was r here, so I put minus 5t. Minus t plus 15t minus 2 equals 0. 14t equals 2. T equals 1/7. Okay, that's t. And so r is minus 5 times 1/7, or minus 5/7. That doesn't simplify, so it's just minus 5/7. So r equals minus 5/7. Okay, we have an r and t value. So first of all, that means we can solve for the points, right? But we want actually the shortest distance. So I guess we solve for the points first. Yeah, let's see what happens. I'll solve for the points. Okay, what did we just solve for? We solved for the t values of a and b so that they're both. What does this have to do? What did I do here? Hold on. Let me think for a second. We don't really have a normal, right? That would be so for the shortest distance between other things, you'd be taking projections. Um, hold on, let me think about this. Okay, I might have to take a moment. Let me look at my other stuff. 141 practice. This was 4.10. Yeah, I did the cross product of the direction vectors. Oh no, this was something else. 4.9. Well, here's me doing it. Oh, I do some sort of projection. Okay, hold on. But then I do this stuff too. So here's me doing this. I found the points. I found S and T. Let me just look at this for a second. 1 plus 2S. 2, yeah. So I did the same thing. I found S and T. Oh, first I found the shortest distance. This is to find the actual point. The shortest distance you do with projections. Let me just check. Let me just see what I'm doing quickly. PQ. Projection of PQ onto. Yeah, makes sense. Okay. Yeah. So what I was doing is kind of for the points. So this would give you the points. I didn't do anything wrong. Like this S and T value, R and T value, give you the points that we're looking for. But to actually find that, to find the shortest distance, yeah, I missed. So, yeah. So let's just choose 2 random points on the line. We can choose this point here. I'll call this one P, call this one Q, right? Say that's P, that's Q. So we can find PQ, and in fact, actually, I'm going to find QP, just because of how I drew it. So maybe I should draw it differently, just so I don't. Oops. Just so I have a match the thing better. So because it won't make a difference. So P, Q. Okay. So let's find PQ. This distance. Wait, is that right? Does that make sense? Hold on, that doesn't make sense. But I did get the right answer on the last one. What I was gonna say is that this distance AB is the projection of PQ onto this vector, right? And that vector is perpendicular to both of these. So it's the component in that direction. Does that make sense? Not really. Yeah, it gives you a perpendicular, right? So if I were to take these 2 lines, they don't intersect, but I were to squish them together so they do intersect, it gives me something perpendicular to both of them. So that if I were to unsquish them, right, this perpendicular is still there, right? And although this one's not touching, it's still going through that perpendicular, the second one. So I unsquished them, right? Yeah, I'll try that. So since I found this point, yeah, I'll try that. So since I found this point, I can actually find the points A and B. So let's find the points A and B. So A was here. So I'll just copy this quickly. So the point A is equal to that. And since we know R now, right? Since we know R is negative 5/7. 3 minus 5/7 is 16/7. So is that one of the answers? Is the first one 16/7? Whoever has the answers. If it's not, then I got to go back. See what I did wrong. So that's point A. Point B is a similar thing. This is point B. Right? So I'll put that up here. So 1 plus T, so 1 plus a 7th, so 8/7. Yeah, okay, so my answer is right. My answer is, yep, the point's right at the bottom of the page. Right? So I'm going to just trust that. Although that last point doesn't make sense. 2 times T is not, oh, what am I? Wow, okay. Oh, I multiplied this in my head. I was like negative 5/7 times 2 is not 2/7, but I'm multiplying the wrong thing. Okay. So my answer is correct. I don't know how they got there, but I don't even want to look at it because I'm going to lose track. So now, for sure, yes, now we can just find the distance between, A and B, right? So I can find, you know what I could have actually done? Just gotten the AB vector, put the numbers in, find the magnitude of that. That's what I should have done. So in fact, I'll just take this. So I will just take this. This is the AB vector, right? So AB, right? Putting in the numbers, so -2, t was 1/7, so -2 plus 1/7 plus 5/7, -8/7, -8/7, 1 minus, so 1 plus 5/7, 12/7, oops, not 17/12, 12/7, and then 2/7 plus 1 minus 5/7, so 4/7. And then we just find the magnitude of this vector, right? So the magnitude of AB is equal to each of those components squared, or square root of each of the sum of each of those components squared. I can never say that right. Yeah, so 8/7, 12/7, 4/7. So 4, let's see, where is it? 4 root something. Yes, 4. Just make sure I did it right. 4 root 14 over 7. So that's the shortest distance, and these are the 2 points. So I actually did it a little bit of a different way than even how I did it before. So first I went for finding those points. Based on those points, I can find the shortest distance. So actually, it's not, I didn't find the shortest distance and then find the 2 points that are that distance apart. I found the 2 distances that are the closest. Yeah, I will for sure. Found the 2 points that are the closest together, right? And then found the distance between them. So to go over quickly, and I did not need actually. Did I need this? I did not need this at all. So I didn't even have to do any projections. No projections here. Right. Okay, so let me go over here. Although there's something that I was just thinking to myself, I did wrong. Of course I didn't, because they got the answer right, but there's something that I either didn't explain properly or, yeah, I didn't use the normal. We'll see. So find the distance between, I'm going to go over everything now. So find the distance between 2 non-parallel lines and find the point on each line that is the closest. Okay, so we have the 2 lines. First of all, just label things. That's P, that's Q, that's L2, that's L1. I'm going to get the parametric forms of both of these lines. Okay, parametric forms. From that parametric form, for both of them, I get an arbitrary point on both. Okay, A and B. I find AB, right, the vector between those 2 arbitrary points, is this. Okay, here is where I found the cross product, which doesn't matter. So what I know about AB, right, this is AB here. What I know is that AB is at the same time going to be perpendicular to the direction vector of this line and the direction vector of this line. Now, the part that's kind of confusing me is, how does that mean the shortest distance? I don't know, I get how that's going to be perpendicular, but no, I guess that does mean shortest distance. So, yeah, I don't know how that means shortest distance exactly. Yeah, so that was actually, I didn't actually end up doing that, right? But you assume that they do not intersect, right? You assume they don't intersect. So that's a good point. That's a good point. If they did intersect, it would be 0, and the closest point would be that point of intersection on both of them. They're you can be non-parallel and not intersect. So of course, I'll show you the options here. If you have, so of course, two lines, they intersect. In R2, sorry, just to be clear, in R2, you cannot have non-parallel lines. Sorry, let me speak a little clearly. In R2, if you have two lines, they can either intersect at a point, they can either be the same line, or they can be parallel. Sure. In R3, it's different. So we're in R3 here. Right, so in R3, you can first of all, it's going to be hard to draw. So you can first of all have just regular parallel lines, right? Or, sorry, just first of all, they can intersect somewhere. Imagine this going in 3D space kind of, and they're kind of coming in and out of the page, right? Then you can also have, of course, the same line again. They can be the same line twice. You can have normal parallel lines that never intersect, right? And then you can have skew parallel lines, right? You can have, so this is up here, and this is down here, right? They're not parallel, and again, it's kind of hard to draw, but this one goes underneath that other one, right? This one goes underneath that other one. Maybe it's better if I just find a picture. Don't mind the calculators. Skew lines in R3. There. These lines are non-parallel, and they do not intersect. These lines are non-parallel, and they do not intersect. This is kind of what I was imagining. That's kind of what I was trying to draw, right? So they're, oh no, those are kind of the planes they make are parallel too, so that's not even a good example. This is, I guess, the best example, right? So yeah. Okay, so I will keep going up here with the explanation. Yeah. So what I did is I knew that both of these would be perpendicular at the same time, right? So that means the dot product would be 0 with each direction vector separately. Gets me two equations, two unknowns. I solve for each unknown, plug that into our generic point. So that gets me the 2 points. Plug that into our generic AB vector. I get the actual AB vector, and then I find the magnitude of that. That's the shortest distance. The key part here is that it's perpendicular to both at the same time. And I'm pretty sure that that's why it's the shortest distance. Although I'm still kind of shaking on that, so maybe not. But I'm pretty sure that's why it's the shortest distance. I mean, I'm not shaking on how to get to the answer, but exactly why? It makes sense that they're both perpendicular. I mean, that it's perpendicular to both. That makes sense. But I'm thinking, are there a bunch of lines? Are there a bunch of points on these two non-intersecting, non-parallel lines? Like, isn't this point and this point, isn't that vector perpendicular to both direction vectors and this vector perpendicular to both direction vectors? Right? But I guess because it's kind of like, it has to be perpendicular. No. So if we just imagine a line, just the direction vectors, and they're like that, then if we want to be perpendicular to this one, that's one thing. Perpendicular to this one, that's another thing. I don't know. I'll have to figure that out. I don't know. But it gets you the answer. It does get you the answer. So perpendicular to both of them. Solve. And there you go. Find the magnitude. But again, why exactly that works, I don't know. Maybe I'll have to watch a 3 blue 1 brown video on it. Probably doesn't have a video on it. But yeah, so that's the answer. Really do be carrying us. Okay, so I can do some other problems. I mean, it's 9 o'clock, so maybe if someone has like one more question, I can do one more question, and then if not, then that's everything. I could do another one from Horowitz's lectures if you want. Yeah. Yeah, for sure. I'll upload it right away. I'll do it right away. And it'll be in my tutor chat on the server at the top. I have tutor announcements. All the way at the top, third thing, right? So it's you can click there, right under announcements. Yeah, I'll do that right after this. So maybe I'll do, if no one has a suggestion, I'll do another one here. Yeah, I'll do another one here for like find the basis. Just find the base, not extend the basis, not extend something into a basis. Just find the basis of this subspace. Right. So the subspace V, unless anyone has any other things, this is just I'm just doing a random question here from Horowitz's lectures. So V is x1, x1, x1? No. x1, x2, x3, x4 in R4, of course, such that x1, wow, I can't write. x1 plus x3 equals 0, x2 plus x3 equals 0, and x1 minus x2 equals 0. So first of all, I want to write this as just a vector with the conditions in it, right? One thing you can notice is that this is actually these conditions are redundant. You have two that actually say the same thing. Two can combine into one, right? So if I just take this bottom one, I could rewrite that as x1 equals x2, right? x1 equals x2. Sure. Well, then I can go up here, right? I can go up here and just put that in for that, right? I can just put x2 plus x, so I replaced x1 with x2. Well, now look, we have two equations that are the same. So actually we only have two criteria here. Right? Okay, so v equals, so x1 equals x2. It doesn't particularly matter actually how I write it, so I just write it as x1, x1, and then x3 equals negative x2. So negative x2, x4. x4 doesn't have any conditions. Okay. And we can write x2 as just x1. Because x2 equals x1. Right? x2 equals x1. Yeah. Yep. That's good. And so now what we can do... Oh, there's another problem, I guess. So now what we can do is this is now one vector, right? So we can write this as a linear combination of basis vectors. Yeah. So I had these three conditions, right? One of them ended up being redundant because I could rearrange the other two to get the last one. So we don't have to actually consider this top one because it's identical to the last one, right? So x1 is x1. I'm going to keep x1 like that. So x1 is x1. x2 equals x1. So I'll put an x1 there. And then from here, I can take this equation, right? I can take this equation, x2 plus x3 equals 0. Rearrange that for x3. x3 equals negative x2. And then apply this as well. x3 equals negative x1. And so that's what I put in the x3 position. Negative x1. And then x4 is x4. So did that make sense? If not, I can explain it differently too. And so... How? Or like where do you type? You can type in discussions, in 141 discussions. And then, yeah, you can see there. So I can find the basis for this just because the basis is the vectors that you can, the linear combination of the basis vectors. Why do you have to sub in for 3 variables? You subbed. Before I subbed in for 1 because I only had one condition. Here. Yeah, here. I only had one condition. So I only sub one variable out. Here I have, well, so I guess that maybe that rule doesn't really work because I have 3 conditions. I guess you just want it in the, yeah, I do have 3 conditions and I subbed in 3 variables. Well, 2 conditions and I subbed in 3 variables. Well, I guess my thinking of it is that I just want it with the lowest amount. I want the lowest amount of different variables here at the same time because I want a linear independent basis at the end. Because the next step here is to say, well, this is a combination of x1 times 1, 1 minus 1, 0, right? Plus x4, 0, 0, 0, 1. So the basis for v is b, which is equal to 1, 1 minus 1, 0, 0, 0, 0, 1. Right, that's a basis for v. If I were to have left x2 in there, not a problem. I could put that in here. This wouldn't be independent anymore. This would have been a dependent set down here. So really I should check if this is dependent or independent. Maybe I'll do that too, just so that I can show that too. So if these are truly independent, that means the only solution of this equation to that equation is a equals 0, b equals 0. So let's try. A equals, well, a equals 0. A equals 0. Negative a equals 0. B equals 0. Okay. Well, then yes, that's the only solution. If we got, for example, infinite solutions, we'd have trouble, right? But here, the only solution for a and b equals 0 is that a and b are both 0. So this is an independent set. So that's a basis for v, right? Maybe let's try it. Let's say I left in this as negative x2, right? So then this would be a 0. This would be a 0. And I'd have a plus x2, 0, 0, minus 1, 0. And so then our basis would have been 1, 1, 0, 0. So we'll go down here. 1, 1, 0, 0. 0, 0, 0, 1. And 0, 0, negative 1, 0. Okay. Oh, sorry. Technically, I wrote that wrong. Shouldn't be a matrix on the outside. I'll fix that. So that is our basis. But we got to check now. Is this independent or dependent? So if this is independent, then the only solution for this 0, 0, 0, 1. Oops, nope, didn't mean to write like that. So the only solution for a times that plus b times that plus 0, 0, minus 1, 0. Plus c times that should be that a equals b equals c equals 0. So let's try. A equals 0. A equals 0. Negative c equals 0. Oh, okay. B equals 0. Okay, hold on. We ran into something. B equals 0. Zero. Well, yeah, this also gives me that. So what am I explaining wrong then? That's our set. How can that possibly be? x1 equals x, yeah. Well, it doesn't actually quite make sense to say, well, no, that should make a difference. That shouldn't make a difference. What I'm thinking is it doesn't make sense to say this because x2 is equal to x1. So this really combines into another thing. It's as if I took. Yeah. So what I'm thinking, that would be my next thing, is that I would have tried to put this in RREF. So let's try that. But what I was just saying is that it would be like taking this first one and splitting into 1, 0, 0, 0. So x1 times that plus x1 times 0, 1, 0, 0. See, like this is technically the same thing, but you'd be giving yourself another basis vector there, right? You'd be giving yourself an extra basis vector. So since this is actually just x1, then those two combine, and then you only have two basis vectors. But why did that not show up in the math here? I was expecting that to be independent. I was expecting this last one to be independent. I was expecting this last one to be dependent. And I did not get that. So my next thing would be, yeah, put this in RREF. Let's see, let's try that. Or just REF. So 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, negative 1, 0. Okay. So, oh boy, wow, I wrote that crooked. Did I write it right? It's 1, 1, 0, 0, 0, 0, 0, 1. Yeah. So row 2 minus row 1. So 1, 0, 0, 0, 0, 0, 0, 0, minus 1, 0, 1, 0. Well, we're already in REF, and it's all the columns. Never mind. So all three. Not at all the result I was expecting. Yeah, but all that means is it means something with the column space, right? It means the column space is 3-dimensional instead of 4-dimensional, but that's all that means. Right. So how is this not a basis? Because it's not a basis. Although I guess it is. No, how is it independent? Yeah, how's that independent? Did I not set this up right? So if I left that as negative x2, it'd be 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, negative 1, 0. Strange. Definitely expected that to be independent. I mean, I keep saying the wrong one. Definitely expected that to be dependent. Yeah, because this would have... Determinant is 0 of this. Of what? Of this? Can you have a determinant of a non-n by n? I guess you can, but I don't know how to do that. A inverse already doesn't exist because A is not an n by n matrix. Yeah. Yeah, I will. Yeah, there's a 0 row. I see. Not quite. Because this is a homogeneous system, so if I were to bring this back into... Does that mean infinite solutions? No, because there's no free variables. That's what I'm thinking. There's no free variables. All our answers are... It's just saying A... Yeah, I see I don't have the right order, but it's pretty much the same thing. We're just saying we're just saying A equals 0, right? So that's from this. Then from this, I'm saying B equals 0. And here I'm saying negative C equals 0. And here I'm saying 0A plus 0B plus 0C equals 0 on that last line. On this line here. That's saying this. Well, I have 3 equations. Yeah, that's how we did it first. That's how we did it first and got the right answer. Yeah, that's how we did it first. And x2 is equal to x1, and then you combine that, and then that's... Oh, so that might be it, because we're only applying... So, because it is x1 over here, but we're applying the condition how we want it. We said we would not apply the condition here, but we do apply the condition here. That's not right. I guess you shouldn't. But how does that make it dependent? That's a good point. Yeah, that could be it. That could be an error we're making here that causes all this to happen. But this is one solution. This is one solution. Because 0, 0, 0, 0, that doesn't add any... Does it add any solutions? No, because there's no free variable. Right, because for there to be infinitely many solutions, we have to say z equals t or something like that, right? We have to say something equals some arbitrary real number. We're not saying that here. If there was an extra column, right? If there was an extra column without a leading entry, that would be infinite solutions. Right? Or like when you're doing when you're doing finding the inverse with the taking A, augmenting it with in, right? To find A inverse. If you had a row of zeros here, that would mean infinite solutions because you're an n by n matrix. This isn't that might be what's confusing. This isn't an n by n matrix anymore. Yeah. So we did find the answer to the question. So I'll go back up to the question here. The question said, well, I didn't write the question, but gave us this subspace. Find the basis of this subspace. So just notice that one of the equations was redundant. You wouldn't actually have that much trouble. Just keep extending. Just keep using the equations, and you'd find that out eventually. Okay, rearrange them and put them into here, right? Rearrange them, put them into here. The actual correct formula here would be x1 minus x1 x4, right? So that's what's supposed to be there. That's what's supposed to be there. I'll explain why it's not in a second, but yeah, because we were testing things. But let's put that there. This should be, so notice here, this is the linear combination that creates any of the vectors here. Notice here that x2 is equal to x1. So these should really combine into one vector here. These should really combine. Yeah, in general, I'm not too worried about this because I know just go for the least amount of variables in this vector here. Form a basis, right? Form a basis here. And then those two vectors that you're doing the combination of, that's your basis. Check if they're independent or dependent. They should be independent. Although we did it. Adding the standard matrix. So that's for adding the standard matrix. That's for saying I have this set B. I have this vector space V. Okay, this B1. The basis, and it says I want you to write the basis of V, where B1 is in the basis, or using B1. That's where you would put the standard matrix. Yeah, so I know it's a little maybe confusing what the question is asking. The question was just asking for a basis of V, any basis of V. Any basis of V. Not using any vectors, not just any basis of V. Right? So the basis would be this. This is the correct answer. This is the correct answer. Yeah. This isn't an extending one. This is just find the basis in the first place. Yeah. Okay. Yeah, so why is that independent? I don't know. I don't know. Maybe I'll try to type up something nice and send it to a teacher and see what they think. Because this is definitely, I can't just send this. I mean, I can send them this video, but I don't know if they have the time to watch that. So, maybe I'll type something up because I would like an answer to this. Any other questions? I think actually someone sent a question, didn't they? Just looking. Okay, so find the vector and parametric equations of the following line. So the lines through that point that meet the line. Ooh, wow. That's a difficult question. I don't know how to do that. Line that goes through that point that meet the line with the vector equation. P is that. Here, I'll save it. Can I just do that? Nope, I guess not. Move that here. The question's asking for here. So write the vector and parametric forms of this line. So the line is goes through that point, meets that line at a distance of 3 from that point. Okay, well, oh, assuming that's on the line? First, I'm going to check if this is on the line. Yes, it's on the line. Sorry, I just noticed it's on the line. So it doesn't... Okay. So our line, first of all, is going to be the vector form of our line is going to start like this. 1, 0, 1, right? Because that's our starting point. Plus t times the direction vector. Okay. That's our starting. Plus r times... t is already used here, and I don't want to use s, so t times the direction vector. That's our line. So we want to hit a point A, that is a distance of 3 from P naught, which is 1, 2, 0. In other words, a P naught, it's going to be difficult to say. I'll just say AP, I guess. The magnitude of this equals 3. What do I do with that? Isn't there? Seems like there would be infinite solutions. Because if we have, unless I'm misunderstanding it, meet the line with that equation, meet that line at points, plural. Oh, the question is looking for all lines. Find the vector favorite equations. No, for the following lines. I'm asking for all lines. Because if you had, what I'm imagining is if you have, this is our point, that's P, this is the line P, okay? We're looking for this globe around it, a distance of 3. Then we have this line over here. Well, it could touch there. It could touch there. Could touch there. Right? It doesn't say that it doesn't say anything about the distance from the rest of P. Right? See Jasper's typing. Hope Jasper has a good idea. Oh, not typing anymore. Lost the... kind of worded really. So at points at distance at 3, so the points meet at points at distance 3, not at 3, yeah, means the direction vector of the line that's given, t2 minus 1 2, that's still a globe of points. That's still like a sphere. I don't say globe. I don't know if I'm saying that. It's still a sphere of points. Or not even a sphere. Well, if you count the line, then it's a circle. But if you count like that we have to touch it with a line, then it's a circle. But for this question here, 1 2 2 1. Let me try to draw it and let's see. Although I don't know how much a drawing would help too much. So we know we have a line. It starts at 1 2 0. Goes in this direction. That direction is 2 negative 1 2. We know 3 away from it is another point. And that we have a line. So you did parallel lines. They don't necessarily have to be parallel. Unless the question says parallel. From up here. No, just the lines. Just ask for the lines. Yeah. Well, assuming they're parallel adds a couple things. Like it adds like, you can do the dot product, should be 0, I guess that's about it. But lets you do projections, I guess, and then you can do projections otherwise too. Well, so I would draw it like this. This line is here. There's a sphere around that. Then we have a line that starts at this point, and it has to cross this sphere and just the edge of the sphere. So these are all the infinite answers. Anything that goes all the way to the sphere just touches the sphere. Then that seems like the answer to me. But so what Jasper said is that t2 minus 1 2. I assume the magnitude of that. The magnitude of the direction vector. Oh, no. I see. Okay. Yep. I see. Yeah. So we have a line. It goes there. It also goes backwards. There's 2 places on it where the distance from P naught is 3. That distance is 3. That distance is 3. We have another line. It starts at some point. We want to know, well, there's still 2 answers. But we want to know this line that passes from here to that point and this point to that point. And those are both the answers. That seems like it's going to work. So pretty much what we're saying is that, so I'll call this, let me see. Okay, I'll explain it a little bit, but I don't know if it's going to work. I don't know if like I sound pretty good on it, but I don't know. So the line that's given is P naught, and then it has a direction vector, right? The line is saying, the question is saying it meets the line. Meets this line at points at a distance of 3. So we don't have a sphere around it anymore. We have 2 points on the line. I mean, the sphere would go around. All these points have a distance of 3, but we're saying it meets the line at a point with a distance of 3 from P naught. From P naught, right? So I'll call this one A and this one B. Our other line, I don't know. I don't. Someone put in the chat. Parthi put in the chat. So, but looks like it's from Nicholson. Looks like it's from Nicholson. Oh, maybe lab 6 or 7. Then I don't know. Oh, okay. So, okay. Well, probably good to look at those. Yeah. So it looks like we're gonna have 2 solutions here. So let's figure out what B is. So B is going to be P naught plus T times the direction vector is B. We don't know T. Well, all we need to know yeah, so what Jasper said is that T times the direction vector, 2, -1, 2. Right? That the magnitude of that is equal to 3. So if the magnitude of that is going to be equal to 3, well, it's just the square root of 2t squared plus -t squared plus 2t. Oops, squared is on the wrong side there. Squared should be outside. And squeeze that in. There you go. 2t squared. That's equal to 3. So 4t squared plus t squared plus 4t squared equals 9. 9t squared. And I got t squared equals 0. T equals 0. So it didn't do anything right there. 9t squared equals 9. Oh, never mind. T squared equals, okay. T squared equals 1. So t equals plus or minus 1. So what that means is that to get to point B, if we just say that's the positive direction, right? Which I did because that's where I put the direction vector. Then point B is P naught plus 1 times the direction vector. P naught plus 1 times the direction vector. And A is P naught minus 1 times the direction vector. It's 1 in the opposite direction. Okay, and so then B, we know these variables. So P naught is 1, 2, 0. So 1, 2, 0 plus, well, I'll write the direction vector. Direction vector was 2, negative 1, 2. Right? So that's 3, 1, 2. Okay, so that's point B. I get technically OB is that, so OB is that. And then OA is going to be the same, so 1, 2, 0 minus the direction vector. So 1 minus 2 is negative 1, 2 plus 1 is 3, 0 minus 2 is minus 2. Okay, so that's point B, point A. So now, well, so it seems like the answer, like, does it have two answers in the solution? Maybe someone has a solution. Yeah. So it seems like the two answer, one answer is going to be, so we have to go through this point, P. We haven't used that yet. 1, 0, 0. Sorry. 1, 0, 1. That's over here. So one line is going to be going from this to here, right? From P 1, 0, 0. Oops, 1, 0, 1. I keep saying the wrong one. To there. So that line I'll call L, and this line I'll call this one L1, this one L2. So the other one's going to go from P to A. Right? So L1 is going to be, right, how we write a vector form of a line is a starting point, 1, 0, 1. 1, 0, 1 is our starting point. Plus T times the direction vector. The direction is going to be PB. PB is going to be our direction vector. That's for the first one. Right? I guess I should have called this one 2 and this one 1, but it doesn't matter. So PB is going to be our direction. PB. And I'll calculate that in just a second. Right? Because I have B and I have P, so I can do that. And then L2 is going to be, so that's our, well, it doesn't matter, is going to be same starting point, but the direction is going to be PA. Oh, I wrote it wrong. PA. So let's actually calculate these things. So PB is I'll calculate up here. PB is B minus P. Right? So B is this. So technically it should be OB minus OP, but it doesn't really matter. So P is 1. So 3 minus 1 is 2. 1 minus 0 is 1. 2 minus 1 is 1. Okay, that's PB. And PA is going to be A minus P. Okay, and that's going to be, where's A? A is here. So 1 minus 1, minus 2. 3 minus 0, 3. Negative 2 minus 1, negative 3. Okay, so we can just put that in. So our answer, L1, is x is equal to 1, 0, 1 plus T times 2, 1, 1. And Jasper, if you have the answer, then let me know if that's right. Or anyone. Not be Jasper, but let me know if that's right. And the other one is 1, 0, 1 plus T times the other one. Negative 2, 3, negative 2. And that's my answer. I don't know if that's right, but it seems like there's solutions. So someone let me know if that's right. And if not, then I'll go find where I made the mistake. Yeah, it's the same thing. It's the same thing. It's just negative 1 times that. Huh? Yeah, so what's what I have? Minus 3 here? Oh, yeah. Sorry, yeah. This is... Oh, yeah, sorry. That's a 3. I just wrote the wrong number. Yeah. So they're probably doing this. I don't want to read it. It's probably doing the same thing I did. Do you want me to go through it? Do you want me to go through from the beginning what I did? Or if anybody wants me to do that. Sure. it's a difficult one. So we're looking for lines that go through point P0101. Oh, I can't read numbers. That meet the line, this line, at a distance of 3 from P naught. Okay, so this is the line P here. I drew it here, right? We want our line, plural, so there's going to be 2 lines, but we want our line to intersect this line, not just anywhere, specifically at a distance of 3 from P naught. So that's P naught. A distance of 3 from it, I'll call this one B. And the other side, there's also a distance of 3. A. A will also have a distance of 3. So what I need to figure out is I need to figure out what multiple of the direction vector will have a magnitude of 3. It's right here. So the magnitude of t times the direction vector equals 3. I'm trying to figure out what that t is, because what that'll do is that'll let me actually find the specific points A and B, right? Because if I figure out, well, so I did it here. So magnitude will be that equals 3, solve for t plus or minus 1. So what that means is that this way is P naught plus the direction vector, plus 1 times the direction vector. And this way is P naught minus 1 times the direction vector. That's this point. That's this point. So I can find exactly those points now. Here, I did it right here, right? So B is that, and P is that, and A is that. I mean. So what I know is that my lines that I'm creating are going to go through 0. Wow, I can't read that point for some reason. 1, 0, 1. Okay. So all of my lines here start. So these are my answers. These are the answers. Start with 1, 0, 1, 1, 0, 1. Right. That's the starting point. Plus t times the direction vector. Well, the first one is going to have a direction PB. Right. PB. And the second one's going to have a direction PA. So I find PB, the vector PB, over here, right? B minus B. And PA, A minus B. And that's my answer. There and there. Yeah. If any part doesn't make sense, I can explain it differently or slower or... No, they're not. All you know is that A and B are on the line, and that the distance from P naught is 3. If we had A and B, then we could just skip right to here, right to PB, we could skip all this, right? But all this is pretty much defined to do this result. This is B, this is A. Right. And then from that, yeah. Difficult question. I'm surprised I could do it. I'm surprised I could just think it out. It was never seen it before, so. Likely it's not going to be on the test. I don't know. They might, I don't know. They give difficult questions. Scroll down. Do you want me to scroll down? Yeah. Maybe I'll zoom out a little bit. So in general, the vector form of a line. Zoom in a little bit. Zoom back in. It's always a pain to zoom back in. Oh, there we go. Is it working? Okay. So in general, the vector form of a line says x is equal to P naught plus TD. Now what this means is that P naught is just a starting point. Right? So I choose any point in space. And I choose some D, direction vector. Okay? Let's just say this. Then this is enough to create a line, because any multiple of that direction vector is going to be a point on the line. For example, 2 times the direction vector. That's going to be 1, 2. This is also a point on the line. 1.5 times. That's also going to be a point on the line. a half a time, negative a half a time, right? Negative, so that would be 1. So negative 2 times would be like over here. And all these points combined, right, this makes a line that goes like this. So you need a starting point, a direction, and then a multiple of that direction. Right? And so then that's what I'm saying here. I'm saying here, line 1. So I knew the answer was that we're going to have 2 answers because there's 2 different points that have a distance of 3. 2 different points that have it. You don't need to. We just need a line. We just need a line, right? Well, it didn't ask us for the distance between like it didn't ask us for this green distance. If it did, then we need to know t. Then we need to figure out what t is. Well, yeah. What we did is we found lines that just pass through, so they keep going, right? They keep going in either direction here, right? But the important thing is that they pass through this line at a distance of 3 from P naught. No problem. Okay, guys. Well, unless there's any more questions, then I'm done for now. No problem. No problem. Good luck. Okay. Okay. Have a good night. Have a good night.